Gravity is the first force ever felt, long before it is named, measured, or questioned. It is present in every step, every breath, every moment of stillness. Objects fall. Bodies rest against the ground. The world feels anchored, stable, and certain. And yet, beneath that familiarity, something quietly resists understanding. Gravity does not look like anything. It has no surface, no texture, no clear direction that can be pointed to and agreed upon. It cannot be switched off, blocked, or isolated. It is felt everywhere, but seen nowhere. And the more carefully it is examined, the less it behaves like the simple downward pull intuition insists upon. If slow questions like this help you unwind, you're very welcome to subscribe and join these gentle explorations. And if you feel like it, you can share where in the world you're listening from tonight. It is always comforting to imagine these thoughts drifting quietly across the planet. For centuries, gravity was treated as something obvious. Apples fell. Planets moved. The explanation seemed almost unnecessary. But as measurements became more precise and observations stretched farther from everyday experience, gravity began to reveal its strangeness. It bent paths instead of pulling directly. It affected time as well as motion. It behaved less like a force and more like a feature of reality itself. Modern experiments show that clocks tick at different rates depending on how close they are to massive objects. Satellites must constantly correct for this effect to keep navigation systems accurate. Entire galaxies move according to gravitational influences that cannot be directly seen, only inferred. And yet, despite this precision, the human mind still struggles to form a clear picture of what gravity actually is. This difficulty is not a failure of intelligence. It is a mismatch between how the brain evolved and the scale at which gravity truly operates. Human intuition was shaped by survival, balance, and immediate cause and effect. Gravity, however, unfolds across vast distances, subtle gradients, and stretches of time far beyond direct perception. It works perfectly, whether it is understood or not. Tonight's journey explores why gravity feels so familiar and yet remains so difficult to imagine. Not as a problem to be solved, but as a quiet example of the limits of intuition. A reminder that understanding does not always mean visualizing, and that clarity can exist without comfort. There is no need to resolve gravity into something simple. It has held the universe together for billions of years without explanation. All that is needed here is attention, curiosity, and the willingness to sit with a force that shapes everything while remaining just out of reach of the mind. Settle in. Let gravity do what it has always done, quietly, relentlessly, without asking to be understood. Long before gravity becomes a word, it becomes a habit. The body learns it the same way it learns breathing or blinking. Slowly at first, through trial and consequence. A toddler leans too far and tips over. A hand reaches for a surface that is slightly too high. A step lands where the ground is not quite where it was expected. Each small mistake teaches the brain something practical. Not what gravity is, but how to live with it. The human brain evolved in a world where falling could injure, lifting required effort, and balance meant survival. Creatures that could quickly adjust posture, sense their own weight, and anticipate motion were more likely to keep moving, feeding, and avoiding danger. Over time, nervous systems became finely tuned to these demands. They did not develop to explain forces, they developed to respond to them. Because of this, gravity enters human experience not as an idea, but as a background condition. It is always there, like temperature or air pressure, shaping everything without announcing itself. The brain treats it less like an object and more like a rule. The ground is down. Objects released from the hand will return to it. Standing upright feels stable. None of this feels remarkable. It simply feels normal. Neuroscience offers a useful explanation for this familiarity. The brain is highly selective about what it brings into conscious awareness. Signals that change suddenly are prioritized. Signals that remain constant are filtered out. This is why a ticking clock fades into silence after a few minutes, and why clothing quickly disappears from awareness once it is worn. Gravity falls into the same category. It is constant, predictable, and therefore easy to ignore. This filtering is not laziness, it is efficiency. At any given moment, the brain is receiving information from millions of sensory receptors. If all of that information demanded attention, decision-making would grind to a halt. Instead, the brain highlights what might require action and suppresses what does not. Gravity, being steady and reliable, is pushed into the background. As a result, gravity is rarely noticed when it is working properly. People do not pause mid-step to admire how well they are being held to the planet. It is only when gravity seems to misbehave that it briefly steps into awareness. A missed stair, a slippery pavement, a glass that unexpectedly meets the floor. In those moments, gravity is no longer invisible, it becomes the culprit. There is something gently amusing about this relationship. Gravity holds oceans in place, keeps the atmosphere wrapped around the planet, and governs the motion of the moon, yet it usually earns attention only when a phone slips from a pocket. It is one of the most influential features of reality, and also one of the most taken for granted. The systems that manage this relationship operate largely outside conscious thought. Deep inside the inner ear are tiny fluid-filled structures that sense orientation and acceleration. These vestibular organs constantly inform the brain about which way is down and how the body is moving relative to it. Muscles adjust automatically. Posture shifts without instruction. Balance is maintained without explanation. As long as these systems function smoothly, gravity feels effortless. Because these adjustments happen automatically, the brain never needs to form a detailed concept of gravity to function. It relies instead on intuition. Intuition is built from experience rather than analysis. It is shaped by what works, not by what is true in a deeper sense. If leaning forward leads to falling, the brain learns not to do that. If lifting something heavier requires more effort, the brain remembers that too. Over time, these patterns solidify into expectations that feel obvious and unquestionable. Psychologists often describe intuition as a shortcut. It allows quick decisions based on past outcomes. This is enormously useful in a dynamic environment, but it comes with limitations. Intuition does not care whether its internal model matches reality perfectly. It only cares whether it produces acceptable results. Gravity, within everyday human experience, behaves consistently enough that a rough model is sufficient. Near the surface of Earth, gravity accelerates falling objects at roughly 9.8 meters per second squared. Engineers use this value routinely. Athletes unconsciously rely on it. The brain absorbs this stability and treats it as a simple fact of life. Things fall. They fall at a predictable rate. There is no immediate reason to question why. This apparent simplicity masks something deeper. The brain evolved to operate within a narrow window of scales. Human intuition is comfortable with distances measured in steps, heights measured in arm spans, and times measured in heartbeats. Gravity behaves politely within this window. Beyond it, intuition begins to strain. The same force that pulls a dropped coin to the ground also guides planets around stars and binds entire galaxies together. But those effects unfold over distances and times far beyond lived experience. Evolution offered no reward for understanding such extremes. There was no advantage in grasping orbital motion or cosmic structure, only in navigating terrain and maintaining balance. As a result, The brain never developed instincts for gravity beyond what daily survival required. It learned to accept gravity as a given, not to interrogate it. Even when formal science entered the picture, intuition remained influential. Early explanations of gravity relied heavily on familiar metaphors of pulling and attraction. These ideas made sense because they echoed bodily experience. A weight pulls on the arm, a load strains the back. The earth, it was said, pulls objects downward. These descriptions were useful, but they quietly reinforced an intuition shaped by muscles and bones rather than by underlying mechanisms. Modern research into perception shows that once an intuitive framework is established, it tends to persist even in the face of new information. Learning more precise descriptions does not erase the original mental model. It sits alongside it. People may understand intellectually that gravity behaves in ways that defy everyday imagery, yet still imagine it as a downward pull because that image feels right. This is why gravity often feels simultaneously obvious and confusing. It is obvious in practice, confusing in explanation. The brain handles it expertly at the level of movement and balance, while struggling to picture what it actually is. This is not a contradiction. It is a reflection of how cognition evolved. Institutions studying human perception and decision-making consistently emphasize this point. The brain is not designed to be a perfect mirror of reality. It is designed to be a functional interface. It highlights what matters for action and downplays what does not. Gravity, being ever present and largely unchanging at human scales, slips beneath notice. Understanding this can be quietly reassuring. Confusion about gravity does not indicate a lack of intelligence or curiosity. It reflects the fact that intuition is a survival tool, not a scientific instrument. The brain is excellent at keeping the body upright and moving. It is less concerned with forming accurate mental pictures of invisible forces. Gravity does not require comprehension to operate. It continues uninterrupted, holding feet to the ground and worlds together, whether it is understood or ignored. Human intuition, shaped by countless generations of practical necessity, simply accepts it as part of the environment. And in that acceptance lies the reason gravity feels so familiar, and yet remains so difficult to truly grasp. When people think about forces, they usually imagine contact. A hand pushes a door, a rope pulls a weight, a foot presses against the ground and the ground pushes back. These interactions feel clear because they involve touch. There is a source that can be pointed to, a direction that can be traced, and a moment when cause becomes effect. The brain is comfortable here. This is the world it evolved to understand. Gravity does not behave like that. There is no surface that reaches up and grabs falling objects, no visible connection between a stone and the earth beneath it. Let go of something and it moves, but nothing appears to act upon it. This absence of contact is the first place where intuition begins to feel uneasy. The brain looks for a source and finds none. Human experience strongly favors forces that announce themselves. Muscles tense when pushing. Skin compresses when something presses back. Even air resistance makes itself known through sound and drag. Gravity, by contrast, operates silently. It leaves no mark, no trail, no sensation that can be isolated from everything else the body's already doing. It is influence without touch, and that alone is enough to make it feel strange. Psychologists studying perception have long observed that the brain prefers explanations with agents. Something causes something else to happen. When an object moves, the mind instinctively looks for what made it move. This instinct works well for everyday interactions, but gravity refuses to cooperate. Nothing is seen to initiate the motion. The object simply begins to fall. To make sense of this, intuition reaches for a familiar idea. Down. Down feels like an answer. It feels directional. It feels grounded. Objects fall down. Rain falls down. People lie down. The brain uses this word as a placeholder for understanding, even though it does not actually explain anything. Down describes orientation, not cause. Pointing downward feels natural because it aligns with bodily experience. Feet are below the head. The ground supports weight. Balance depends on knowing where down is relative to the body. But this sense of direction is local, not universal. Down points toward the center of the Earth, not toward a fixed direction in space. On the opposite side of the planet, down points the other way. Both feel equally correct. This already places strain on mental models. If gravity came from the ground, then the ground would need to pull equally in all directions. That idea quickly collapses. The ground beneath one person is not beneath another person thousands of kilometers away. Yet gravity acts on both without conflict. The source cannot be the surface. This leads to a subtle but important shift. Gravity does not act from the ground upward. It acts from mass itself. The Earth does not pull objects because they are near its surface. It influences them because it has mass, and that mass extends inward toward the planet's center. This idea is conceptually difficult because it lacks a clear boundary. Where does the Earth's influence begin? Where does it end? There is no sharp edge. The effect weakens with distance, but it never fully disappears. Even far beyond the atmosphere, the Earth's presence is still felt. Physicists describe this weakening with distance using a mathematical relationship that can be written in words as the force of gravity between two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. This relationship, formalized by Isaac Newton in the late 17th century, allows precise predictions, but it does not provide a satisfying mental picture. It tells how gravity behaves, not what it looks like. The lack of a visible source continues to trouble intuition. If gravity does not come from the ground, and it does not travel through a medium that can be sensed, then where is it? The brain is left without a location to anchor the idea. It floats, untethered, resisting imagery. This discomfort is amplified by everyday language. Words like pull and attraction imply contact or intent. They suggest that something reaches out. Gravity does neither. There is no arm extending from the Earth, no thread connecting objects. The influence is present everywhere at once, diminishing smoothly with distance, indifferent to obstacles. Scientific bodies studying fundamental forces emphasize that gravity is unique in this respect. It cannot be blocked. It cannot be screened. There is no known material that stops it from passing through. Mountains, oceans, and entire planets offer no resistance. Gravity acts as if everything is transparent. This property alone makes gravity deeply unintuitive. Most forces experienced in daily life can be interrupted. A wall stops a push. A barrier redirects motion. Gravity ignores all of this. It acts regardless of what lies between objects. The brain, accustomed to barriers and boundaries, struggles to accommodate a force that respects none. There is also the matter of direction. When an object falls, it accelerates toward the Earth's center, not toward the surface beneath it. This distinction matters, but it is rarely noticed. At human scales, the difference between straight down and slightly inward is imperceptible. Intuition smooths it over. But once attention is drawn to it, the picture begins to warp. Consider standing on a vast plain. Down feels vertical. But if lines were drawn from that point toward the center of the planet, and then from another point hundreds of kilometers away, those lines would not be parallel. They would converge. Gravity does not point in one universal direction. It points inward, everywhere. This realization quietly undermines the simple idea of down as a global concept. It reveals that what feels like a single direction is actually many directions at once, all oriented toward mass. The brain did not evolve to think this way. It evolved to think locally. Historically, even scientists found this difficult to accept. Newton himself was uneasy about gravity acting at a distance without contact. He famously refrained from speculating about its underlying cause, focusing instead on describing its effects. Later physicists would continue this tradition, prioritizing accurate prediction over comforting explanation. Modern physics has refined this picture further, replacing the idea of force with geometry, but the discomfort remains. Gravity still lacks a clear source in the way intuition expects. There is no switch that turns it on, no location where it begins. It simply exists as part of how massive objects relate to one another. This absence of a source is not a failure of understanding. It is a reflection of the limits of everyday experience. The brain expects causes to be local, visible, and directional. Gravity offers none of these. It operates silently, universally, and without contact. Yet despite this conceptual strain, gravity remains perfectly reliable. Objects fall, orbits persist, structures stand. The universe does not hesitate because intuition is uncomfortable. It continues to behave according to rules that do not require approval. The difficulty lies not in gravity itself, but in the expectation that every influence must have a tangible origin. Gravity challenges that expectation gently but persistently. It asks the mind to accept influence without touch, direction without pointing, and presence without location. For a brain shaped by hands, feet, and surfaces, that is a tall order. And it is here, in this quiet absence of a source, that gravity begins to feel less like a familiar force and more like something that resists being pinned down at all. Dropping an object feels like one of the simplest things a person can do. Open a hand, release the grip, and the object falls. There is no hesitation, no uncertainty. It does not wander sideways or pause to consider alternatives. It moves with confidence, as though it knows exactly where it is going. This reliability makes falling feel obvious, almost trivial. It feels like the kind of event that needs no explanation at all. Because it feels so obvious, the mind rarely lingers on it. A dropped coin does not invite reflection. It invites retrieval. The brain notes the outcome, adjusts behavior if necessary, and moves on. Falling becomes part of the background rhythm of life, as familiar as footsteps or breathing. But the moment an explanation is requested, simplicity dissolves. Why does the object fall at that speed rather than another? Why does it begin moving immediately rather than slowly gathering momentum? Why does it follow a straight path downward instead of drifting or curving? These questions appear innocent, but they quickly lead away from everyday intuition and into abstraction. Early explanations often begin with mass. Objects have mass, and mass is involved in gravity. This sounds manageable. Heavier things feel different when lifted. They resist motion. They press down more firmly on the hand. Mass is already part of bodily experience, so the word feels familiar, even comforting. But mass is not weight. Weight depends on gravity. Mass does not. This distinction already nudges intuition out of its comfort zone. An object with the same mass will feel lighter on the Moon and heavier on Jupiter, even though nothing about the object itself has changed. The brain can accept this fact intellectually, but it struggles to picture what mass is doing independently of weight. Attraction is often introduced next. Objects attract one another. The Earth attracts the object. This language helps, but only briefly. Attraction suggests intention or direction. It implies something reaching out. Gravity does not reach. It does not choose. It does not pull harder because something is closer in a deliberate sense. It simply behaves according to consistent rules. Acceleration follows soon after. A falling object does not move at a constant speed, it accelerates. Each moment, it moves faster than the last. Near the surface of Earth, this acceleration is remarkably consistent. Measurements show that objects increase their downward speed by about 9.8 meters per second every second, regardless of their mass, assuming air resistance is minimal. This fact has been confirmed countless times, from early experiments in the 17th century to modern laboratory measurements. It is one of the most reliable numbers in physics, and yet, while the number is precise, it does little to help the imagination. Saying that something accelerates at 9.8 meters per second squared does not produce a picture. It produces a rule. This highlights a quiet divide between physics and intuition. Physics is content with numbers. Intuition prefers images. Numbers excel at describing patterns. They allow predictions to be made and tested. Engineers rely on them to build bridges and design vehicles. Astronomers use them to chart the motion of planets. The success of these efforts demonstrates that the descriptions are accurate even when they feel abstract. But numbers are not experiences. The brain does not feel 9.8 meters per second squared. It feels effort, balance, and motion. When an explanation relies on quantities rather than sensations, intuition begins to disengage. The explanation may be understood intellectually while remaining emotionally unsatisfying. This is not a flaw in physics, it is a feature of how the brain works. Psychological research shows that the mind is far better at handling relative comparisons than absolute values. Heavier, lighter, faster, slower. These comparisons map easily onto lived experience. Exact quantities require symbolic reasoning, which operates in a different cognitive space. This is why explanations of falling often feel clearer when described comparatively, even if they are less precise. Consider the familiar idea that heavier objects fall faster. Intuition supports this. A feather drifts, a stone drops. It feels obvious. Yet controlled experiments show that when air resistance is removed, objects of different masses fall at the same rate. This result surprises many people, not because it is complicated, but because it conflicts with expectation. The conflict arises from experience rather than ignorance. In daily life, air resistance matters. The brain learns from what it observes. It builds a model that works well enough most of the time. When physics removes air from the situation, intuition is left holding the wrong assumptions. This gap between observation and explanation widens as descriptions become more refined. Physics explains falling not as a response to being released, but as motion through a gravitational field. The object is already moving, in a sense, even before it is dropped. Once support is removed, it follows the natural path available to it. This way of speaking can feel unsettling. It suggests that the object was never truly at rest, that standing on a table is not a natural state, but a constrained one. The table prevents motion that gravity would otherwise produce. Letting go does not cause the fall, it allows it. This reversal of cause and effect is subtle, but it matters. Intuition imagines falling as something that starts when the hand opens. Physics describes it as something that was always trying to happen. Once again, numbers make this clear while imagination resists. The equations governing motion show smooth, continuous change. They describe trajectories without drama. But the mind prefers events. It looks for beginnings and endings, for moments where something happens. Falling, in physical terms, is not an event. It is a process. This is one reason why visualization often fails. There is no simple picture that captures acceleration, mass and gravitational influence all at once. Diagrams can show arrows and curves, but they are symbolic. They stand in for relationships rather than depicting mechanisms. Scientists are well aware of this limitation. Many have pointed out that understanding does not require visual imagery. Some of the most successful physicists have reported thinking primarily in terms of relationships, patterns, and mathematical structures rather than pictures. The absence of a clear mental image does not prevent accurate reasoning. This idea can feel counterintuitive, especially in a culture that values seeing as understanding, but gravity resists being seen. It demands a different kind of acceptance, one where explanation does not produce a comforting picture, but a reliable framework. There is quiet humour in how confidently objects fall compared to how uncertain explanations become. A dropped mug never hesitates. It does not ask how gravity works, it simply obeys. Meanwhile, entire libraries exist attempting to describe why that obedience occurs. The success of physics lies in its willingness to accept this imbalance. It does not insist that understanding must feel intuitive. It accepts that some aspects of reality operate beyond the brain's evolved preferences. Numbers are used not because they are satisfying, but because they are effective. This realization can be freeing. It removes the pressure to imagine gravity perfectly. It allows understanding to exist as familiarity with behavior rather than clarity of image. Knowing how something behaves, how it responds, and how to predict its effects can be enough. Falling feels simple because it is reliable. Explaining it feels difficult because it exposes the limits of intuition. The gap between those two experiences is not a failure of comprehension. It is a reminder that the universe does not organize itself for human comfort. Gravity continues to guide every fall with calm consistency, indifferent to whether it is pictured or not. The mind, meanwhile, does what it has always done. It adapts, approximates, and moves forward, carrying useful knowledge even when the deeper picture remains just out of view. Down feels dependable. It is the direction feet point toward, the way objects return when released, the orientation that keeps the body upright and comfortable. From early childhood, the brain builds its sense of space around this idea. Down is not just a direction. It is a reference point. It anchors movement, balance, and expectation. This confidence begins to unravel the moment space enters the picture. Images of astronauts floating effortlessly inside spacecraft are often described as scenes of weightlessness. Pens drift, water forms shimmering spheres, bodies glide without effort. To intuition, this looks like gravity is simply switched off. Space, it seems, is a place where down no longer exists. That interpretation feels natural, and it is almost entirely wrong. Astronauts in orbit are not beyond gravity's reach. In fact, they are very much within it. At the altitude of the International Space Station, gravity is only slightly weaker than it is on the surface of Earth. Measurements show it remains close to 90% of its surface strength. If gravity truly stopped there, the station would drift away. Instead, it circles the planet every 90 minutes with remarkable regularity. The key to this apparent contradiction lies in understanding orbit not as hovering, but as falling. Orbit is a continuous fall that never reaches the ground. This idea sounds counterintuitive at first, because falling is usually associated with impact. But falling in physical terms simply means moving under the influence of gravity without support. When a spacecraft enters orbit, it is given a sideways speed so great that as it falls toward Earth, the planet curves away beneath it. The spacecraft keeps missing the ground, tracing a path around the planet rather than into it. This is why astronauts float. They are falling at the same rate as their spacecraft. Everything inside is accelerating together. There is no surface pushing up against their feet, no chair pressing back against their bodies. Without that contact force, the familiar sensation of weight disappears. Weight, it turns out, is not the same thing as gravity. Weight is what you feel when something prevents you from falling. Standing on the ground, the earth pushes upward on the body. That upward force is what muscles and bones register as weight. In orbit, there is no such push. Gravity is still acting, but nothing resists it. The body responds by drifting, not because gravity is absent, but because it is unopposed. This distinction is subtle, and it collides directly with everyday experience. On Earth, gravity and weight always appear together. Whenever gravity acts, the ground is there to respond. The brain merges the two concepts into one. Gravity becomes synonymous with heaviness, pressure, and downward force. Space breaks that association cleanly. Without floors or chairs, the brain loses its primary reference for down. Orientation becomes ambiguous. Astronauts report that up and down lose meaning within hours. What matters instead is forward, backward, left, and right relative to the spacecraft. Down ceases to be a universal direction and becomes a local convenience. This loss unsettles intuition. The brain insists that gravity must end somewhere because it has learned to associate gravity with standing. If standing is impossible, gravity must be gone. That conclusion feels logical, but it rests on a false assumption. Gravity does not depend on surfaces. It does not originate from floors or ground beneath the feet. It acts through space itself, shaping motion regardless of whether anything is there to push back. Scientific bodies involved in spaceflight have repeatedly emphasized this point when explaining orbital mechanics to the public. Astronaut training materials carefully avoid the term zero gravity for this reason. Instead, they describe microgravity, acknowledging that gravity is present but its effects are masked by constant free fall. This constant falling creates an environment where familiar cues vanish. Liquids do not pool. Flames burn differently. The inner ear struggles to orient the body. Motion sickness is common during the first days in orbit as the brain tries to reconcile conflicting signals. Vision says floating is normal. Balance systems insist something is wrong. The discomfort highlights how deeply gravity is woven into perception. The brain expects down to behave consistently. When it does not, confusion follows. Everyday experience reinforces the idea that gravity weakens with height. Climb a ladder and the ground feels farther away. Stand on a mountain and the world seems more open. These experiences subtly suggest that gravity might thin out above the surface. In reality, the change is small. Even at several hundred kilometers above Earth, gravity remains strong enough to dictate motion. What changes is not gravity itself, but how motion unfolds under its influence. The brain's insistence that gravity must stop in space reflects its preference for boundaries. Things begin here. Things end there. Forces switch on and off. Gravity refuses to follow this pattern. It fades gradually with distance, never reaching a clear edge. This gradual weakening is difficult to accept because it offers no dramatic transition. There is no moment where gravity gives a farewell wave and disappears. Instead, it stretches outward indefinitely, influencing motion across vast distances. Planets feel the pull of the sun. Moons respond to planets. Stars orbit galactic centers. The same influence governs all of it. Once this continuity is acknowledged, the idea of down becomes local rather than universal. Down on Earth points toward the planet's center. Down near the moon points elsewhere. In orbit, down points inward, but motion sideways keeps changing where inward leads. This realization dismantles the notion of a single cosmic down. It reveals direction as something relative, not absolute. The brain, accustomed to stable frames of reference, struggles with this flexibility. There is gentle humor in how confidently people gesture upward when talking about space. as though space were a location above rather than all around. This habit reflects how deeply Earth-based intuition shapes language. Space feels like a direction, because gravity trained the brain to think that way. Physics quietly disagrees. From its perspective, there is no privileged orientation. Motion depends on relationships, speeds, and masses, not on up or down. Gravity shapes paths, not directions. It guides motion inward, but inward is defined locally, not globally. Astronauts adapt to this quickly. Within days, floating feels natural. Movement becomes effortless. Orientation becomes a matter of choice rather than necessity. The brain, given time, learns a new normal. This adaptability reveals something important. Intuition is flexible, but it requires experience. On Earth, intuition is shaped by constant contact with surfaces. In orbit, new patterns emerge. The brain updates its expectations, even as it remains unable to picture gravity in a satisfying way. Down breaks in space not because gravity fails, but because familiar cues disappear. What remains is the underlying influence, steady and impartial, guiding motion without announcing itself. Gravity does not stop at the edge of the atmosphere. It does not retreat into the planet. It continues outward, shaping orbits and trajectories with quiet persistence. The mind's expectation of an ending point dissolves, replaced by a smoother, stranger reality. Understanding this does not require visualizing invisible lines or forces. It requires accepting that everyday experience is a narrow sample of a much broader pattern. Gravity behaves the same everywhere. It is intuition that changes. Once that shift is made, floating astronauts no longer represent an absence of gravity. They become a demonstration of it, a reminder that falling does not always look like falling, and that down, for all its familiarity, is only a local habit of mind. Gravity feels powerful when it pulls a person toward the ground, yet strangely weak when compared to many other forces encountered in daily life. A small magnet can lift a paperclip against the entire mass of the Earth. A gentle push can slide a book across a table despite the planet's constant pull. These experiences quietly suggest that gravity is somehow feeble, easily overpowered, and perhaps less important than it truly is. This impression comes from scale. At human sizes and distances, gravity is subtle. It acts consistently but not dramatically. Its effects accumulate slowly, almost politely. The brain, tuned to notice sharp changes and immediate causes, tends to overlook influences that work gradually. Gravity does its most important work over distance and time, not through sudden intervention. Magnets offer a useful contrast. Magnetic forces feel immediate and decisive. Bring two magnets close together and the effect is obvious. They snap together or push apart with unmistakable urgency. The interaction is visible, tactile, and localized. The brain has no trouble assigning cause and effect. Something nearby is doing something noticeable. Gravity does not announce itself this way. Between small objects, its influence is extraordinarily weak. Two people standing side by side exert a gravitational pull on each other, but the effect is so tiny that no instrument built for everyday use could detect it. The brain registers nothing at all. This weakness at small scales is not a flaw in gravity. It is a consequence of how it behaves. Gravity depends on mass, and everyday objects contain very little of it compared to planets or stars. A magnet's strength, by contrast, arises from electromagnetic interactions within atoms, forces that are far stronger than gravity at short distances. Physicists have measured this difference precisely. When comparing fundamental interactions, gravity is vastly weaker than electromagnetism. This is why a refrigerator magnet can defy the pull of the Earth without difficulty. The magnet does not need to be powerful in an absolute sense. It only needs to act over a very short distance, where gravity's influence is minimal. The brain takes this experience at face value. If a small object can overpower gravity so easily, gravity must be weak. This conclusion feels reasonable, but it misses the bigger picture. Gravity's strength reveals itself not through intensity, but through persistence. Unlike many forces, it never cancels out. Positive and negative electric charges can balance one another. Magnetic fields can oppose and neutralize. Gravity only attracts. There is no opposite mass to counteract it. Every piece of matter contributes, and nothing subtracts. This property allows gravity to dominate at large scales. While it is easily overshadowed between atoms and small objects, it becomes decisive when enormous amounts of mass are involved. Planets form because countless particles all pull inward together. Stars ignite because gravity compresses matter relentlessly. Galaxies assemble because gravity works patiently across immense distances. The brain struggles with this kind of accumulation. Human intuition excels at judging immediate strength, but performs poorly when effects build slowly over time or space. This limitation appears in many contexts. People underestimate the impact of small daily habits, the gradual rise of compound interest, or the slow warming of a changing climate. Gravity belongs to this same category. Its power lies not in forcefulness, but in endurance. At the surface of Earth, gravity accelerates objects downward at about 9.8 meters per second squared. This value feels modest when experienced moment to moment. A falling object does not slam instantly into the ground. It gains speed gradually, but over a few seconds that steady acceleration produces significant motion. Over planetary scales, the effect becomes overwhelming. Consider the Earth itself. Its mass is so large that its combined gravitational influence holds an atmosphere thousands of kilometers thick, keeps oceans pressed against its surface, and guides the Moon along a stable path. None of these outcomes arise from sudden action. They result from countless tiny pulls acting together, continuously without interruption. The brain is not naturally equipped to sense this kind of collective influence. Evolution favored perception tuned to immediate threats and opportunities. A falling branch, a charging animal, a shifting surface. Gradual influences were less urgent. As a result, intuition discounts them. This scale blindness feeds misunderstanding. Gravity appears weak because its effects at human scale are easy to overlook. The mind assumes that what feels weak locally must be weak universally. Physics reveals the opposite. Gravity becomes dominant precisely because it acts everywhere, on everything, all the time. Scientific organizations studying planetary formation emphasize this point repeatedly. Models of star and planet formation show that gravity, despite its relative weakness between individual particles, governs the large-scale structure of the universe. It is the architect of cosmic order, shaping systems that endure for billions of years. Everyday experience hides this truth. When lifting a grocery bag, muscles strain against gravity and succeed. When pushing a chair, friction and force quickly overcome it. These interactions teach the brain that gravity is negotiable. What they do not teach is that gravity is cumulative. There is gentle humor in how easily gravity is dismissed. A person might casually flick crumbs off a table, casually defeating the gravitational pull of an entire planet, and conclude that gravity is not much of a challenge. Meanwhile, that same force is holding continents in place and guiding oceans around the globe. The problem is not ignorance, it is perspective. The brain evolved to function within a narrow window of scale, where gravity behaves quietly and predictably. Outside that window, intuition loses its footing. It cannot easily grasp forces that reveal their strength, only when multiplied by vast amounts of mass and time. Understanding gravity therefore requires a shift in emphasis. Instead of asking how strong it feels, it helps to ask how consistently it acts. Instead of focusing on dramatic moments, it helps to consider accumulation. Gravity is not impressive because it overwhelms nearby objects. It is impressive because it never stops. Once this is recognized, the magnet and the planet no longer seem comparable. The magnet wins locally, briefly, and within a limited range. Gravity loses those small contests, but wins the long game. It shapes worlds. The brain's difficulty with this idea is deeply human. It reflects a preference for immediacy, clarity, and visible cause. Gravity offers none of these at small scales. It whispers rather than shouts. Yet those whispers add up. Over time, over distance, and across unimaginable quantities of matter, gravity becomes the dominant influence. The universe takes its shape not from the strongest force in any given moment, but from the one that persists when everything else fades. Recognizing this does not require abandoning intuition. It requires placing intuition in context. Gravity feels weak because human experience samples only a tiny fraction of its reach. Beyond that narrow slice, a different story unfolds, one written not in sudden motion, but in steady accumulation. And it is there, at scales far beyond everyday life, that gravity finally reveals just how powerful it has been all along. When gravity is placed alongside the other fundamental forces of nature, its oddness becomes clearer. The universe operates through a small set of interactions that govern how matter behaves. Some of these interactions feel familiar, immediate, and controllable. Gravity does not belong comfortably in that group. Electromagnetic forces are the most noticeable in everyday life. They're responsible for light, electricity, magnetism, and the solidity of matter itself. Every time a light switches on, a phone charges, or a magnet snaps to a refrigerator door, electromagnetic forces are at work. They act strongly over short distances and weaken quickly with separation. They can attract or repel. They can be blocked, redirected, and switched off. Nuclear forces are even more intense, though far less visible. The strong nuclear force binds protons and neutrons together inside atomic nuclei. Without it, atoms would not exist. The weak nuclear force governs certain types of radioactive decay, shaping how elements change over time. These forces act only at extremely small distances, inside atoms and subatomic particles. They are powerful, precise, and deeply tied to the structure of matter. Gravity stands apart from all of this. It is vastly weaker than the other forces when measured at small scales, yet it dominates the universe at large scales. It does not repel. It does not cancel itself out. It does not switch off. It does not respect barriers. There is no known material that blocks it, no orientation that avoids it, no configuration that neutralizes it. This makes gravity uniquely stubborn. Electromagnetic forces can be shielded. A metal enclosure blocks electric fields. Magnetic forces can be redirected using carefully arranged materials. Even radiation can be absorbed or scattered. Gravity ignores all such attempts. It passes through walls, mountains, oceans, and planets as though they were not there. The Earth's core, dense and extreme, offers no resistance to gravity's influence on objects at the surface. This property alone sets gravity apart conceptually. Most forces announce themselves through interaction. They push back when pushed. They respond to obstacles. Gravity does not. It acts without contact and without interruption. This behavior frustrates intuition. The brain expects influence to diminish when something gets in the way. If a wall blocks light, it should block other effects too. Gravity refuses to cooperate. The wall does nothing. The force continues as if the wall were absent. Physicists describe gravity as acting universally on mass and energy. Anything with mass participates. Nothing opts out. This universality gives gravity its cosmic importance, but it also makes it difficult to explain in familiar terms. There is no special case. There is no exception that intuition can cling to. Another difference lies in direction. Electromagnetic forces depend on charge. Positive and negative charges attract or repel in ways that feel symmetrical. Nuclear forces depend on very specific conditions inside atomic nuclei. Gravity depends only on mass. Every mass attracts every other mass. The simplicity of this rule is deceptive. It hides complexity behind uniformity. Because gravity only attracts, it cannot be balanced in the same way other forces can. Electric charges can cancel. Magnetic fields can oppose. Gravity accumulates. Every contribution adds to the total effect. This accumulation is what allows gravity to shape stars, galaxies, and the large-scale structure of the universe, despite its weakness between individual particles. The brain struggles with this asymmetry. It expects balance. It expects forces to compete visibly. Gravity competes quietly, winning only because it never stops competing. This quiet persistence contributes to gravity's isolation within physics. While electromagnetic and nuclear forces fit neatly into a framework based on particle interactions and exchanges, gravity resists that treatment. Attempts to describe it in the same language encounter difficulties. The rules that work so well elsewhere do not translate cleanly. This has been recognized for decades. Physicists can describe gravity's effects with extraordinary precision, predicting planetary motion, satellite trajectories, and the bending of light near massive objects. Yet describing what gravity is, in the same terms used for other forces, remains elusive. This conceptual isolation feeds confusion. If gravity behaves so differently, perhaps it is not really a force at all. Perhaps it belongs in a different category. This line of thinking has shaped much of modern theoretical physics, leading to descriptions that move away from pushing and pulling entirely. From the perspective of everyday intuition, this is deeply unsettling. Forces are supposed to do things to objects. They are supposed to act through contact or exchange. Gravity seems to act through presence alone. The inability to shield gravity reinforces this unease. If gravity cannot be turned off, then it cannot be experimented with in the same way as other forces. Conditions cannot be isolated. Variables cannot be removed entirely. Gravity is always part of the system, whether it is wanted or not. This makes it difficult to study directly and even harder to explain intuitively. Many experiments rely on detecting tiny differences rather than clean on and off comparisons. The brain prefers contrasts. Gravity offers continuity. There is gentle humour in how casually gravity is discussed compared to how fundamental it is. People speak of escaping gravity as though it were something left behind, like a city boundary. In reality, spacecraft never escape gravity entirely. They move from one gravitational influence to another, trading one dominant presence for another. Gravity's refusal to be excluded gives it a quiet authority. It does not compete for attention. It does not flare or fade. It simply remains. Scientific organizations studying fundamental interactions often emphasize that gravity's uniqueness is not a flaw in understanding, but a clue. Its difference suggests that it may not belong in the same conceptual box as other forces. Treating it as an outlier rather than an anomaly opens new ways of thinking. For the brain, however, this uniqueness feels like isolation. Gravity does not behave the way forces are expected to behave. It does not respond to intuition's demands for locality, direction, or control. It does not offer handles to grab onto. This is why explanations of gravity often feel unsatisfying, even when they are accurate. They describe behavior, without providing a mechanism that intuition recognizes. They ask the mind to accept influence without exchange and action, without contact. And yet, gravity's strangeness is precisely what makes it essential. Its universality binds the universe together. Its persistence gives structure to time and space. Its refusal to be switched off ensures stability across immense scales. Understanding gravity therefore requires a shift in expectation. It is not a stronger version of familiar forces, it is something else entirely. Its behavior cannot be reduced to pushing, pulling, or shielding. It must be accepted on its own terms. The brain, shaped by forces that act locally and visibly, finds this difficult. Gravity remains conceptually isolated because it does not match the patterns intuition prefers. It operates everywhere, all at once, without interruption. In that sense, gravity is not just another force among many. It is the quiet framework within which all other forces operate. It does not announce itself because it does not need to. Everything else already moves within its reach. And it is this silent, unyielding presence that continues to place gravity just outside the boundaries of easy understanding, even as it holds the universe together with unwavering consistency. Language is usually the bridge between experience and understanding. It gives shape to thoughts, allows ideas to be shared, and turns sensation into explanation. But when it comes to gravity, language begins to strain. Words that work well for everyday actions start to bend under the weight of something far less familiar. Most explanations of gravity begin with metaphors. Gravity pulls, objects attract, space bends. These phrases are useful because they borrow from experiences the brain already knows. Pull-ins suggest effort. Attractions suggest closeness. Bending suggests shape. Each metaphor offers a handhold, a way into an idea that would otherwise feel unreachable. At first, this works remarkably well. Saying that the Earth pulls objects downward produces an immediate sense of cause and effect. Describing gravity as attraction helps explain why masses move toward one another. Talking about bending helps convey why paths curve rather than remain straight. These images allow the mind to engage without needing technical detail. The problem is that metaphors do not stay in their place. The brain tends to treat them not as approximations, but as descriptions. A pull becomes something imagined as muscular or elastic. Attraction becomes something intentional, almost emotional. Bending becomes a picture of space behaving like rubber or fabric. Over time, these images harden into expectations, and those expectations begin to mislead. Gravity does not pull in the way hands pull. There is no tension, no stretching, no exertion that can be felt or traced. Attraction does not involve desire or direction. Objects do not seek one another out. And space does not bend in the way a sheet bends over a table. These metaphors point toward relationships, not mechanisms, but intuition often mistakes them for literal explanations. This confusion is not accidental. Language evolved to describe human-scale experiences. It excels at naming objects, actions, and relationships that involve bodies, tools, and environments. Gravity operates far outside this domain. It acts across empty space, over immense distances, and through influences that leave no sensory trace. Language reaches for what it knows and falls short. Physicists are keenly aware of this limitation. Many have noted that the mathematics describing gravity is far more precise than any verbal explanation. Equations capture relationships cleanly, without committing to imagery. They specify how quantities change and interact, not what they look like. This precision allows predictions to be made with extraordinary accuracy. For example, the motion of a falling object can be described using the distance fallen equals 1/2 multiplied by gravitational acceleration multiplied by time squared. Written this way, the relationship is clear to someone trained to read it. It tells exactly how distance depends on time, but spoken aloud, it becomes cumbersome. And imagined visually, it offers little guidance. This gap between mathematical clarity and verbal vagueness creates a dilemma. Most people do not think in equations, they think in stories and pictures. When equations are translated into words, something is lost. Relationships become narratives, quantities become qualities, precision gives way to familiarity. Simplification is often necessary, especially in education. Concepts must be introduced gently. Technical detail can overwhelm, but simplification carries risk. Each layer removed introduces assumptions. Each metaphor chosen excludes alternatives. Over time, these choices accumulate into mental pictures that feel coherent, but do not quite match reality. Consider the common image of space as a stretch fabric, with massive objects creating dents that guide motion. This metaphor has been widely used because it provides an intuitive way to picture curved paths. Objects roll inward because the surface slopes. The image is compelling and memorable. It is also incomplete. The fabric analogy relies on gravity itself to work. The dent only forms because gravity pulls the fabric downward. Without gravity, the demonstration fails. More importantly, space does not require an external direction to bend into. There is no down for it to sag toward. The metaphor quietly imports assumptions that do not belong. Yet despite these flaws, the image persists because it offers something intuition craves. It offers shape. It offers direction. It offers a picture. Language often does this. It trades accuracy for comfort. This trade is not unique to gravity. It appears whenever abstract ideas are expressed in everyday terms. Economies are described as growing or shrinking. Time is said to flow. Electricity is said to run through wires. In each case, the metaphor helps initially and hinders later. With gravity, the hindrance becomes especially noticeable because the subject resists imagery so strongly. No single metaphor survives scrutiny. Each one captures an aspect while distorting another. Pulling suggests force but implies contact. Attraction suggests connection but implies intent. Bending suggests geometry but implies materiality. Scientists often respond by layering metaphors, hoping that together they will triangulate the truth. Gravity pulls objects but not like muscles. Space bends but not like fabric. Objects attract but not deliberately. These caveats accumulate until the explanation becomes hedged and hesitant. At this point, frustration can set in. If no description is quite right, perhaps understanding is impossible. But this conclusion rests on an assumption that understanding must be pictorial, that to know something is to see it clearly in the mind's eye. This assumption is not required. Many areas of science operate comfortably without imagery. Probability, for example, is rarely visualized directly. People learn to work with likelihoods and distributions without picturing them as objects. The same is true for dimensions beyond the familiar three, or for quantum properties that have no classical counterpart. Understanding takes the form of knowing how systems behave, not what they resemble. Gravity belongs in this category. It can be understood as a set of relationships rather than a thing. Objects move the way they do because of how mass, distance, and time relate. These relationships can be described, measured, and tested. They do not require a picture to be valid. Accepting this requires a shift in expectation. It asks for comfort with partial descriptions, with explanations that are correct without being complete in an intuitive sense, with language that gestures rather than depicts. There is gentle humour in how stubbornly the mind clings to imagery. Even after learning that metaphors mislead, people continue to use them, often with apologies attached. Space bends, sort of. Gravity pulls in a way. The qualifiers reveal awareness of the problem without offering a solution. Perhaps the solution is not to find better metaphors, but to loosen the demand for them, to allow language to describe behaviour without insisting on form, to accept that some aspects of reality are best approached through patterns rather than pictures. Scientific bodies involved in physics education increasingly emphasise this point. They encourage learners to focus on relationships, predictions, and consistency rather than mental images. This approach may feel less satisfying at first, but it proves more stable over time. Gravity does not suffer from a lack of explanation. It suffers from an excess of imagery. Each metaphor competes for attention, and none can claim full accuracy. Letting them coexist lightly and provisionally may be the most honest approach. Language will always fall short when describing something as fundamental and abstract as gravity. It was never designed for that task, but falling short does not mean failing. It means pointing. Words can guide attention, frame questions, and set boundaries. They can indicate where intuition applies and where it does not. They can prepare the mind for ideas that cannot be pictured cleanly. Understanding gravity may never feel like holding a clear image. It may feel more like recognizing a pattern in motion, a consistency across situations, a quiet reliability that does not need to be visualized to be trusted. In that sense, language does not need to succeed completely. It only needs to succeed enough to move thought forward, enough to dissolve confusion into familiarity, enough to allow gravity to be known not as a picture, but as a dependable part of how the universe behaves. Comfort with that kind of understanding does not come naturally. It is learned slowly, through exposure and reflection. But once it settles in, the need for perfect metaphors fades. Gravity remains what it has always been: steady, universal, resistant to simple description. Language may stumble around it, but the underlying relationships remain intact. And perhaps that is enough. The idea that space itself can be curved is often where understanding begins to slow down. Not because it is especially complicated, but because it asks the mind to release one of its most deeply held assumptions, that space is flat, straight, neutral, a passive stage on which events unfold. From early life, perception reinforces this assumption. Floors look level, walls rise vertically, horizons stretch out in straight lines. Movement feels simplest when it follows a direct path. The brain grows comfortable with flatness because flatness works. It allows distance to be judged, balance to be maintained, and motion to be predicted with minimal effort. This comfort comes at a cost. Flat thinking dominates perception because it is efficient, not because it is accurate at every scale. Human environments are small compared to planets. Human journeys are short compared to orbits. Over these limited distances, curvature is difficult to detect. The surface of the Earth feels flat because the Earth is enormous relative to the body. Curvature hides itself well. As a result, the brain treats flatness as the default. Curves are seen as features added onto an otherwise straight world. Hills rise from flat ground. Roads bend where necessary. Arches curve for decoration or strength. Curvature feels optional, an exception rather than a rule. This intuition carries over into attempts to understand gravity. When curved space is introduced, it is often received as a strange embellishment, a clever idea layered on top of more familiar concepts, something decorative rather than structural. Space, the mind insists, should be straight by default. Any bending must require explanation. This resistance is natural. Curvature is usually associated with visible shape, a bent branch, a curved surface, a bowed beam. These forms curve into something else, into surrounding space. They have an inside and an outside. They bend relative to a background that remains flat. Curved space does not work this way. There is no surrounding space for it to curve into, no external direction that defines the bend. This is where imagination falters. The brain looks for a reference frame and finds none. It tries to picture space sagging, dipping, or warping downward, only to realize there is no down for space itself. This confusion is often reinforced by common explanations. Popular descriptions sometimes suggest that massive objects dent space, like a heavy ball placed on a stretched sheet. The image is vivid and memorable. It provides a way to picture curved paths without invoking equations. It also introduces a quiet misunderstanding. In that picture, something outside the sheet pulls the fabric downward. Gravity itself is used to explain gravity. The demonstration works only because it borrows a force it is meant to describe. More importantly, it suggests that space bends toward an external direction, when in reality there is no such direction available. Nothing is sagging into anything else. Curvature in this context is not a shape imposed on space. It is a property of space itself. Distances, angles, and paths behave differently than they would in a flat geometry. Straight lines, defined as the shortest paths between points, do not behave the way intuition expects. They curve, not because something pushes them, but because the underlying structure they pass through is not flat. This idea feels abstract because it lacks a sensory anchor. There is no texture to curved space, no resistance, no visual cue. Everything appears normal locally. A small region of curved space looks indistinguishable from a flat one, just as a small patch of the Earth's surface appears flat to someone standing on it. This local flatness is crucial. It explains why everyday experience offers no hint of curvature. At human scales, space behaves almost exactly as intuition predicts. Only when distances grow large, or when precision becomes extreme, do the differences appear. Scientific measurements confirm this subtlety. Experiments involving the motion of planets, the bending of light near massive objects, and the ticking rates of clocks at different heights all reveal effects that align with curved geometry rather than force-based pulling. These results are consistent, repeatable, and precise, yet they do not translate easily into imagery. The mind resists because it wants curvature to be something added on, a distortion layered atop an otherwise straight world. In reality, curvature is foundational. It determines how motion unfolds from the outset. Objects do not move and then get deflected. They follow the natural paths available to them. This reframing challenges another deeply held assumption. That straightness is fundamental. In Euclidean geometry, straight lines are privileged. They define shortest distance. They set expectations. In curved geometry, straightness becomes local rather than global. What counts as straight here may not remain straight elsewhere. This shift can feel unsettling. It removes the comfort of a universal reference. The brain prefers absolutes. It wants to know which direction is straight everywhere. Curved space offers no such guarantee. Curvature also feels decorative because it is often introduced late as an advanced concept. Students first learn physics in flat space, where forces act and trajectories are drawn against a neutral background. Curved space arrives later, wrapped in new language and new mathematics, and feels like an add-on rather than a replacement. In truth, curved space is not an extra feature. It is a different description of the same behavior, one that removes the need for invisible pulls acting across distance. Motion becomes a response to structure rather than force. This is not ignorance resisting correction. It is intuition resisting reorganization. The brain built its spatial understanding to navigate terrain, not geometry. It expects space to be a container, not an active participant. Asking it to treat space as something that can influence motion is a fundamental change in perspective. Importantly, this difficulty does not indicate a lack of intelligence. Many highly trained scientists have noted that curved space is easier to work with mathematically than to imagine conceptually. The mathematics is clean. The intuition lags behind. That lag is not a failure. It reflects the limits of sensory-based thinking. Curved space does not announce itself through sensation. It reveals itself through patterns, through consistency across experiments, through agreement between theory and observation. Understanding emerges from recognizing those patterns, not from seeing a shape. Once this is accepted, resistance softens. Curvature no longer needs to be visualized. It can be treated as a rule governing how distances and times relate. A quiet framework rather than a picture. This perspective allows gravity to be understood without invoking sagging fabrics or invisible pulls. Objects move as they do because they are following the structure available to them. Space and time provide that structure. The human mind may never find this description emotionally satisfying. It may always prefer stories of force and direction. But satisfaction is not the same as accuracy. Curved space challenges intuition because it removes the familiar scaffolding of flatness. It replaces surfaces with relationships, directions with local definitions, causes with structure. That challenge is not a weakness in explanation. It is an invitation to expand what understanding can look like. Understanding does not have to feel like a picture snapping into focus. It can feel like a rule settling into place. A quiet acceptance that reality does not always arrange itself around human expectations. Curved space is difficult not because it is obscure, but because it is subtle. It does not shout. It does not distort the everyday world in obvious ways. It quietly guides motion while leaving appearances intact. The brain, shaped by surfaces and straight lines, naturally resists this subtlety. That resistance is human. It is expected. Recognizing it as a conceptual limit rather than a personal failure changes the tone of the struggle. Confusion becomes understandable, resistance becomes reasonable, and understanding becomes something broader than imagery. Space does not bend in order to be seen. It bends because that is how relationships between mass, motion, and time are organized. The universe does not require the mind to picture it correctly in order to function. Accepting curved space is less about mastering a concept and more about releasing a demand. The demand that everything meaningful must be easily imagined. Once that demand loosens, curved space no longer feels decorative. It becomes structural, not something added to reality, but something quietly shaping it from within. And in that shift, gravity begins to make a different kind of sense. Time feels steady in everyday life. Seconds pass one after another. Clocks agree with one another. Yesterday stays behind, tomorrow waits ahead. This regularity is so reliable that time is often treated as a background condition, much like gravity once was. It is there, always moving forward, rarely questioned. Gravity quietly disrupts this comfort. According to modern physics, time does not pass at the same rate everywhere. Its flow depends on gravity. Clocks tick at different speeds depending on how strongly gravity acts upon them. Closer to massive objects, time moves more slowly. Farther away, it speeds up. The difference is small, but it is real, measurable, and unavoidable. This idea tends to provoke unease, not because it is complicated, but because it violates expectation. Time is supposed to be universal. It is meant to march forward in lockstep, unaffected by location or circumstance. Gravity interfering with time feels like a category error. Gravity pulls on objects. Time flows. The two should not mix, yet they do. Experiments performed over the past century have confirmed this effect repeatedly. Highly precise atomic clocks placed at different heights tick at slightly different rates. A clock closer to the surface of Earth runs more slowly than one placed higher up. The difference is tiny, amounting to fractions of a second over long periods, but the consistency is undeniable. This phenomenon is known as gravitational time dilation. It arises because gravity influences not just motion, but the structure of time itself. Where gravity is stronger, time progresses more slowly. Where it is weaker, time passes more quickly. For intuition, this is deeply unsettling. Time has no weight. It cannot be held or dropped. It leaves no footprint. The idea that gravity, which already resists visualization, can reach into something as intangible as time feels like an overreach. The mind looks for a boundary and finds none. Real-world technology, however, does not have the luxury of ignoring this effect. Satellites orbiting Earth experience weaker gravity than objects on the surface. As a result, clocks aboard those satellites tick faster than identical clocks on the ground. The difference is not theoretical. It accumulates quickly enough to cause serious problems if left uncorrected. Navigation systems rely on precise timing to determine position. Signals sent from satellites include timestamps that receivers use to calculate distance. If satellite clocks were allowed to run freely, without accounting for gravitational time dilation and other relativistic effects, positioning errors would grow by several kilometers each day. Roads would shift, locations would drift, navigation would become unreliable. To prevent this, engineers deliberately adjust satellite clocks so that they remain synchronized with clocks on Earth. The corrections are built into the system from the start. Gravity's influence on time is not an abstract curiosity. It is an operational necessity. Despite this, everyday life offers no hint of time behaving strangely. People do not notice time moving faster upstairs than downstairs. Lunch does not arrive earlier on a hilltop. Conversations do not drift out of sync between floors of a building. The differences are too small to register without specialized equipment. This invisibility contributes to discomfort. The brain expects cause and effect to be obvious. When something cannot be felt or seen, it is easy to dismiss. Gravity-altering time does not announce itself through sensation. It reveals itself only through careful measurement. The mind prefers time to be simple, because simplicity makes planning possible. Memories rely on sequence. Language depends on shared timing. Social life assumes that now means roughly the same thing for everyone involved. The idea that time could behave differently depending on location threatens this shared framework, even if the threat is purely conceptual. Part of the unease comes from how time is usually imagined. It is often pictured as a river flowing at a constant rate, carrying everything along. Gravity disrupting that flow suggests bends, slowdowns, and variations that defy the metaphor. Once again, language and imagery struggle to keep up. Physics does not share this discomfort. From its perspective, time is not an independent backdrop. It is part of a connected structure influenced by mass and motion. Gravity changes the relationships between events, including their timing. This description works mathematically and matches observation, even if it refuses to settle into a comfortable picture. The human brain, however, evolved to operate on short timescales and small distances. It didn't need to account for clocks drifting apart due to gravity. Survival depended on knowing when to act, not on synchronizing atomic oscillations across altitudes. Intuition therefore treats time as uniform because uniformity was good enough. This mismatch between lived experience and physical reality mirrors earlier difficulties with gravity itself. In both cases, the brain relies on patterns that work locally and consistently. When those patterns are extended beyond their original domain, cracks appear. There's gentle irony in how gravity reveals its influence on time only through precision. The effect becomes visible only when clocks are accurate enough to notice it. As measurement improves, reality becomes stranger. What once appeared absolute becomes conditional. Scientists often point out that nothing about this behavior is dramatic in practice. Time does not lurch or stutter, it flows smoothly everywhere, just at slightly different rates. There is no moment when someone steps into a stronger gravitational field and feels time slow. The effect accumulates quietly, second by second, unnoticed. This subtlety makes it harder to accept. The brain is attuned to events, not gradients. It looks for moments of change. Gravity's effect on time offers none. It operates continuously, gently adjusting rates without fanfare. The discomfort this produces is not fear, but disorientation. It challenges the idea that time is separate from the physical world. It suggests that time is woven into the same structure as space and motion. For intuition, this is a radical proposal. Everyday language reinforces separation. Time passes, gravity pulls, space contains, physics dissolves these boundaries. It treats time as something that can stretch, slow, and vary depending on context. Understanding this requires letting go of simple categories. Importantly, this does not mean everyday experience is wrong. Time behaves uniformly enough at human scales that treating it as constant is entirely reasonable. The corrections required are tiny. Life proceeds as expected. Schedules hold, memories form. The trouble arises only when intuition is asked to account for extremes, high precision, high speeds, strong gravity. Under those conditions, assumptions that once worked begin to fail. The unease that follows is a signal, not a flaw. It marks the boundary where evolved intuition gives way to measured reality. The brain is encountering a domain it was never designed to navigate unaided. Gravity affecting time is unsettling because it dissolves a familiar separation. It reveals that the universe does not organize itself according to human categories. Time is not protected from physical influence. It participates. Recognizing this does not require imagining clocks slowing visibly or time thickening like syrup. It requires accepting that some relationships exist beyond direct perception. They reveal themselves only through careful comparison and accumulated evidence. Once this acceptance settles in, the discomfort softens. Time does not become chaotic or unreliable. It remains orderly, just not uniform. Gravity does not disrupt daily life. It quietly fine-tunes it. Everyday experience hides these effects because it can afford to. The margins are small. The differences are negligible. Only when precision matters does gravity's reach into time become visible. The brain, encountering this truth, does what it always does when intuition fails. It resists, then adapts. It learns to hold two ideas at once. Time feels steady and time varies. Both are true within their domains. Understanding gravity's effect on time therefore becomes less about visualizing a strange phenomenon and more about adjusting expectation. Reality is consistent but not always simple. The discomfort comes from expecting simplicity where none was promised. Gravity does not merely guide motion. It shapes the tempo of existence itself, quietly, steadily, without asking permission. Time continues to flow. Clocks continue to tick. Life continues uninterrupted. Beneath it all, gravity adjusts the pace, revealing once again that intuition, for all its usefulness, was never meant to grasp the universe in full. If gravity was simple, physicists would not still be arguing about it. Not arguing in the sense of disagreement over data, but in the quieter, more persistent sense of how best to describe what's going on, how to frame it, how to think about it, how to speak about it without misleading. The surprising part is not that disagreement exists, it is that it exists even where agreement is overwhelming. Physicists agree on how gravity behaves in countless situations. They can calculate planetary motion with extraordinary precision. They can predict the paths of spacecraft, the bending of light near massive objects, and the subtle shifts in time measured by atomic clocks. The mathematics works. The predictions match observation. Technology depends on it every day. And yet, when asked what gravity is, the answers begin to diverge. Some descriptions treat gravity as a force, similar in spirit to other forces but acting universally. Others describe it as geometry, a feature of how space and time are structured. Still others frame it as an emergent effect, arising from deeper principles not yet fully understood. Each description captures something true. None captures everything. This plurality can feel unsettling. The brain prefers singular explanations. One story, one picture, one definitive answer. When experts offer multiple descriptions, intuition interprets this as uncertainty or confusion. In reality, it reflects the limits of representation. Gravity resists being contained within a single mental picture because it operates across domains that do not align neatly. At everyday scales, treating it as a force works well. Objects fall, trajectories curve, engineering calculations succeed. At larger scales, or where time itself becomes involved, the force picture begins to creak. Geometry offers a cleaner account. Paths follow structure rather than responding to pulls. Neither picture is wrong. Each is incomplete. This incompleteness is not a flaw unique to gravity. It appears throughout science whenever a phenomenon spans multiple scales or frameworks. Light behaves as a wave in some contexts and as particles in others. Matter can be described as solid in daily life and as mostly empty space at atomic scales. The descriptions change because the questions change. With gravity, the shift is particularly stark because intuition is already strained. There is no comfortable image to fall back on. The mind looks for a single, authoritative explanation and finds a family of them instead. Physicists are open about this. Many have emphasized that current descriptions of gravity work extraordinarily well within their domains, while still leaving deeper questions unanswered. The theories are powerful, but they are not final. They describe relationships, not ultimate causes. This openness can be mistaken for doubt. It is better understood as humility. Science advances by refining models, not by declaring them complete. A model is judged by how well it predicts and explains within a given range. When that range is exceeded, new descriptions are developed. Old ones are not discarded so much as placed in context. Gravity sits at an intersection where multiple models overlap without fully merging. Classical descriptions handle motion and structure at human and planetary scales. Relativistic descriptions handle extreme precision and strong fields. Attempts to unify gravity with other fundamental interactions remain works in progress. This situation invites debate, discussion, and careful disagreement. Not because the science is failing, but because it is being honest about its scope. For listeners, this can be reassuring rather than troubling. Confusion about gravity is not a personal shortcoming. It is shared by the field itself. The most knowledgeable people in the world do not claim to hold a single, intuitive picture that resolves every question. Instead, they work with tools, mathematical frameworks, conceptual models, approximations that are valid here but not there. Understanding becomes something layered rather than unified. The brain often resists this layered approach. It wants closure. It wants to know which description is correct. The answer, unsatisfying as it may seem, is that correctness depends on context. This does not mean anything goes. The descriptions are not arbitrary. They are constrained by evidence and consistency. They overlap where they must and diverge where they can. The disagreement lies not in the data, but in interpretation and emphasis. There's gentle humour in how often gravity is described as the simplest force, while simultaneously being the most debated. It falls under everything, yet refuses to settle into a single explanation. The simplest action, letting go of an object, connects to some of the deepest questions in physics. This tension highlights an important feature of scientific understanding. It is not built around comfort. It is built around reliability. A theory does not need to feel intuitive to be trusted. It needs to work. Physicists are comfortable holding ideas that lack clear mental images. They work with symbols, relationships, and abstractions because those tools deliver results. The absence of a picture does not prevent progress. In many cases, it enables it. For non-specialists, this can feel like standing outside a conversation conducted in a foreign language. But the essence of the conversation is accessible. It revolves around acknowledging limits, recognizing where intuition applies and where it does not, accepting that some aspects of reality are best approached indirectly. Scientific bodies often emphasize this perspective when communicating complex ideas. They stress that uncertainty does not equal ignorance, that multiple models can coexist without contradiction. That debate is a sign of active understanding, not failure. This framing matters because it shifts the emotional tone of confusion. Instead of feeling excluded, listeners can recognize themselves within a broader human effort to understand something that resists simplification. Gravity challenges not just individual intuition, but collective imagination. It exposes the gap between lived experience and cosmic behavior. It reminds even experts that description is not the same as depiction. Humility emerges naturally from this recognition. Not humility as self-doubt, but as proportion, an awareness of how much can be known, how much can be predicted, and how much remains open. This humility does not weaken science. It strengthens it. It keeps models flexible. It invites revision. It prevents premature closure. For the listener, there is comfort in knowing that difficulty is not a personal failure. Struggling to picture gravity does not mean something has been missed. It means the mind is encountering a boundary. That boundary is not fixed. Over time, familiarity grows. Concepts that once felt alien become workable. Understanding deepens, even if imagery never fully arrives. Gravity remains an example of how knowledge can be precise without being pictorial, how agreement can exist alongside debate, how confidence can coexist with uncertainty. Physicists argue about gravity not because they are lost, but because they are attentive. They are exploring the edges of what their tools can describe. They are careful with claims. They resist oversimplification. In this sense, shared confusion becomes a feature rather than a flaw. It keeps inquiry open. It encourages patience. It aligns expectations with reality. Understanding gravity is not about finding the one correct mental picture. It is about learning which descriptions apply where, and why none of them stand alone. Once that expectation settles in, the arguments stop feeling troubling. They begin to feel appropriate, a sign that the subject is deep enough to deserve careful thought. Gravity continues to behave with remarkable consistency, whether or not its description is unified. Objects fall, orbits persist, time shifts subtly, the universe holds together. Human understanding advances alongside this stability, refining its language, adjusting its models, and accepting that some questions invite ongoing conversation rather than final answers. And in that ongoing conversation, confusion is not an outsider. It is a companion. Humans do not experience the world as empty space filled with objects. They experience it as a collection of surfaces, floors that support weight, horizons that define distance, walls that mark edges. Even before language develops, the brain organizes reality around these features. A surface is something that can be stood on, leaned against, or moved around. It offers stability and orientation in a way that open space does not. This reliance runs deep. From an evolutionary perspective, surfaces meant safety. Solid ground allowed movement without falling. Edges signaled danger. Horizons provided information about terrain, weather, and approaching threats. Creatures that could quickly interpret these cues were more likely to survive. Over time, nervous systems became exquisitely sensitive to contact with surfaces and to the directions those surfaces implied. Gravity enters this story not as a force to be understood, but as an orienting signal. It tells the body which way is stable. It defines which surfaces can be trusted. Feet press downward. Heads remain above shoulders. The world organizes itself vertically around this constant influence. In this sense, gravity is less about pulling and more about orientation. It defines up and down not as abstract directions, but as lived experience. The brain does not calculate gravitational influence explicitly. It infers it from contact, from pressure on the soles of the feet, from tension in muscles, from the way balance feels when upright versus tilted. These signals are processed automatically. Deep within the inner ear are fluid-filled structures that respond to acceleration and orientation. They detect changes relative to gravity without conscious effort. When the head tilts, the fluid shifts. Nerve signals adjust posture. Muscles respond before thought intervenes. Balance is maintained as a reflex, not a decision. This system evolved long before abstract reasoning. It does not ask why gravity exists. It only asks whether the body is aligned with it. Because of this, surfaces become central to perception. A floor is not just a place to stand. It is confirmation that gravity is behaving as expected. A horizon is not just a line in the distance. It is reassurance that space is organized in familiar ways. Edges provide warnings. They tell the brain where support ends and risk begins. Everyday life reinforces this dependence. Chairs support weight, stairs guide movement, roads define direction. Even screens and pages provide visual surfaces that organize attention. The brain grows accustomed to a world that is reliably bounded and oriented. Space removes all of this. In orbit, there is no floor pressing upward, no horizon separating ground from sky, no edge where support clearly ends. The visual field offers few cues about orientation. Objects float rather than rest. Bodies drift rather than stand. The familiar partnership between gravity and surfaces dissolves. Importantly, gravity has not disappeared. What has disappeared is resistance. Without a surface to push back, the sensation of weight vanishes. Muscles relax, bones unload. The signals the brain normally uses to define up and down fall silent. The inner ear still detects movement, but without a stable reference, its messages become ambiguous. This ambiguity produces discomfort, especially at first. Astronauts often experience disorientation and motion sickness during the early days of spaceflight. The brain receives conflicting information. Vision suggests stillness. Balance systems signal motion. Muscles report weightlessness. The usual agreement between senses breaks down. This reaction is sometimes described dramatically, but it does not need to be. It is not fear. It is confusion. The brain is trying to apply rules that work perfectly on Earth to an environment where those rules no longer apply. It expects surfaces. It expects pressure. It expects gravity to announce itself through contact. When none of that happens, it struggles to build a coherent picture. Over time, adaptation occurs. The brain learns new patterns. It recalibrates expectations. Floating becomes normal. Movement becomes effortless. Orientation becomes flexible rather than fixed. Up and down lose their importance, replaced by forward and backward relative to the body or spacecraft. This adaptation highlights how much of gravity's presence is inferred rather than sensed directly. On Earth, gravity is felt because it presses bodies into surfaces. In space, that pressure is gone, and with it goes the feeling of gravity, even though gravity itself remains. This distinction often surprises people. It reveals how closely gravity and surfaces are intertwined in experience. Gravity without surfaces feels like no gravity at all. The brain's need for surfaces also shapes how gravity is imagined. People often picture gravity as something that comes from below, as though the ground itself were responsible. This makes sense from a bodily perspective. The ground is where pressure is felt. It is where support originates. The idea that gravity acts from mass rather than surfaces feels abstract, because it bypasses the sensory cues the brain relies on. Even language reflects this bias. Phrases like being grounded, standing on solid ground, or having one's feet on the floor all link stability to surfaces. Gravity is implied but rarely named. It works silently in the background, organizing experience without explanation. When surfaces disappear, that organization collapses. The brain loses its primary reference points. Discomfort arises not because gravity is strange, but because the environment no longer supplies the cues intuition expects. This helps explain why space feels unsettling even when danger is absent. Floating looks peaceful, yet the lack of orientation can be deeply disorienting. The mind searches for edges and finds none. It looks for down and receives no answer. Importantly, this reaction is not a failure of adaptation. It is evidence of how specialized human perception is. The brain evolved to operate in a world of surfaces shaped by gravity. Remove those surfaces, and perception must work harder. Scientific studies of long-duration spaceflight show that while adaptation occurs, some effects persist. Muscles weaken without regular loading. Bones lose density. The body itself depends on gravity mediated through surfaces to maintain structure. The need for contact is not merely perceptual, it is physiological. This reinforces the idea that gravity's most immediate role in human life is not as an abstract force, but as an organizer of interaction. It defines how bodies meet the world. It shapes posture, movement, and sensation through constant contact. Understanding gravity as orientation rather than pull helps make sense of these experiences. Gravity tells the body how to arrange itself relative to surfaces. Remove the surfaces, and gravity becomes harder to feel even if it continues to act. The discomfort that follows is therefore unsurprising. It is the result of a deeply ingrained expectation being unmet. The brain is not confused because it is limited. It is confused because it is specialized. This perspective removes drama from the experience. There's nothing mysterious or threatening about losing orientation in space. It is simply the nervous system operating outside its usual conditions. Given time, it adjusts. The same principle applies to understanding gravity more generally. Intuition relies on surfaces because that is where gravity announces itself most clearly. When explanations move away from surfaces and into abstraction, intuition loses its footing. Recognizing this helps reframe confusion. Difficulty picturing gravity is not a lack of insight. It reflects the fact that human perception was built for a world where gravity always came with flaws, horizons, and edges. Space strips those away, revealing how much of understanding depends on contact. The unease that follows is not fear of the unknown. It is the quiet protest of a brain that has lost its reference points. Gravity remains present, steady and reliable. What changes is the way it is felt. Surfaces give gravity a voice. Without them, it speaks too softly for intuition to hear. Gravity is not only something people observe, it is something they feel. Every moment spent standing, sitting, or lying down comes with a quiet bodily reminder that weight exists. Muscles tense to support posture. Feet press into the floor. Shoulders carry the mass of arms and head. This constant sensation makes gravity feel personal, almost intimate, woven directly into experience rather than imposed from outside. Weight is one of the earliest physical sensations learned. Long before words like force or mass exist, the body discovers effort. Lifting feels different from lowering. Holding something heavy demands attention. Fatigue arrives sooner when weight increases. These experiences teach the brain what gravity feels like, not what it is. Because of this, gravity becomes associated with the body itself. It is not an abstract influence acting at a distance. It is pressure in the joints. It is strain in the muscles. It is the reason standing upright feels different from lying down. The brain treats these sensations as direct evidence of gravity, even though they're only indirect effects. This bodily grounding gives gravity emotional weight as well. Language reflects this connection. People describe difficult times as heavy. Relief is described as lightness. Burdens weigh on the shoulders. Letting go feels like lifting something off the chest. These expressions are not accidental. They borrow from the physical experience of gravity to describe internal states. Psychologists have long noted that abstract concepts are often built on physical metaphors. The mind uses familiar sensations to organize less tangible experiences. Gravity, because it is always present, provides a rich source of such metaphors. Heaviness becomes associated with seriousness, effort, or sadness. Lightness becomes associated with ease, freedom, or joy. This emotional layering reinforces the sense that gravity is personal. It does not just shape motion, it colors meaning. The problem arises when physical feeling is mistaken for explanation. The sensation of weight feels like gravity itself, but it is not. Weight is the result of gravity interacting with surfaces and resistance. It is gravity translated into pressure and effort. The distinction is subtle but important. On Earth, this translation is so consistent that it goes unnoticed. Gravity and weight appear inseparable. Wherever gravity is, weight is felt. The brain fuses the two into a single experience. Gravity becomes synonymous with heaviness. This fusion makes abstraction difficult. When gravity is described in terms that do not involve weight, intuition rebels. Talking about gravity acting on objects that are floating, or affecting time, or shaping space itself feels disconnected from lived experience. The mind searches for pressure, strain, or downward force and finds none. The explanation feels incomplete, even if it is accurate. Physical feeling interferes because it is compelling. Sensation feels more trustworthy than description. Muscles do not lie. Joints do not speculate. If gravity feels like heaviness, then heaviness must be gravity. This reasoning is understandable but limited. Consider astronauts in orbit. Gravity continues to act on their bodies, yet they feel weightless. Muscles relax. Bones unload. The familiar sensation disappears. If gravity were identical to weight, it would have vanished. But it has not. What has changed is the presence of resistance. This example highlights the gap between felt gravity and described gravity. One is experiential, the other is relational. One depends on contact and support, the other does not. The brain struggles to hold these two ideas simultaneously. It wants gravity to feel the same way everywhere. It wants sensation and description to align. When they do not, confusion follows. This confusion is intensified by how closely gravity is tied to identity. Weight is experienced through the body, and the body is central to self-perception. Anything that acts on the body feels personal by default. Gravity presses on everyone equally, yet it is felt individually. Each body responds according to its own mass, posture, and strength. This individual experience makes gravity feel subjective, even though it is not. Two people standing side by side experience different levels of effort depending on fitness, fatigue, and size. Gravity itself has not changed. The bodily response has. Separating these layers requires deliberate effort. It means recognizing that sensation is not explanation, that what the body feels is a translation, not the source. Scientists often emphasize this distinction when discussing gravity. They point out that gravity acts on mass, not on feelings. The equations describing gravity do not include muscle strain or fatigue. They describe relationships between masses, distances, and time. The body enters the picture only when resistance is involved. This does not make bodily experience irrelevant. It makes it contextual. The same principle appears in other areas of perception. Temperature is felt through skin, yet temperature itself is a measure of average molecular motion. Sound is heard as tone and volume, yet it is vibration moving through a medium. Sensation provides access, not definition. Gravity is no different. The emotional associations attached to heaviness and lightness add another layer of interference. Because heaviness often carries negative connotations, gravity can feel oppressive. Because lightness feels pleasant, weightlessness is often imagined as freeing. These feelings shape expectation and color interpretation. In reality, gravity is indifferent. It does not care whether it feels comforting or burdensome. It acts uniformly, regardless of emotional response. The meanings attached to heaviness arise from human experience, not from gravity itself. Understanding this helps loosen the grip of sensation on explanation. It allows gravity to be seen as something that interacts with bodies without being defined by them. The body becomes one participant in a broader system, rather than the reference point for all understanding. This shift can feel unsettling at first. It asks the mind to step back from its most reliable source of information, but it also opens space for clarity. Once sensation is recognized as translation, not essence, explanations that once felt abstract begin to settle. Gravity affecting time no longer needs to feel heavy. Curved space does not need to press downward. Motion guided by structure does not need to strain muscles. The separation is gentle, not abrupt. Sensation does not need to be discarded. It simply needs to be placed in context. There is quiet humor in how stubbornly gravity feels personal. Even after learning that weight is not gravity itself, people continue to describe gravity in bodily terms. It pulls, it presses, it holds things down. These phrases persist because they are grounded in experience. They are useful as long as they are recognized as metaphors. Scientific understanding does not require abandoning bodily intuition. It requires supplementing it, recognizing where intuition applies and where it does not, allowing different descriptions to coexist without demanding that they feel the same. Gravity feels personal because it is always acting on the body, but it is not personal in its nature. It does not single out individuals. It does not respond to effort or emotion. It operates according to relationships that remain the same regardless of who is experiencing them. Gently separating sensation from explanation allows both to coexist. The body can feel weight. The mind can understand gravity. Neither needs to replace the other. Once this separation is accepted, confusion softens. Gravity no longer needs to feel right in order to be understood. It can be trusted to behave consistently, even when sensation tells only part of the story. The feeling of weight remains a useful guide for living. The description of gravity remains a reliable guide for understanding. Each has its place. gravity continues to act, quietly and impartially, whether it is felt as heaviness, imagined as pull, or described as structure. The personal experience belongs to the body. The explanation belongs to the universe. Keeping those roles distinct makes room for both comfort and clarity. At cosmic scales, gravity behaves in a way that feels almost unrecognizable compared to everyday life. There are no sudden drops, no sharp impacts, no dramatic falls. Instead, motion unfolds slowly, across vast distances and over immense stretches of time. What looks like stillness to human perception is often movement so gradual that it escapes notice entirely. Galaxies are not fixed objects hanging in space. They are in motion, bound together by gravity into graceful rotating systems. Stars orbit galactic centers over hundreds of millions of years. Entire galaxies drift toward one another, drawn together into clusters that span millions of light years. Nothing about this motion is hurried. Nothing snaps or collapses suddenly. Gravity works patiently, shaping structure through accumulation rather than forcefulness. This slowness is one of the main reasons gravity feels so different at large scales. Human intuition expects action to be immediate. A push produces movement. A release produces a fall. Cause is followed quickly by effect. At cosmic scales, the delays are so long that the connection becomes hard to see. Consider a pair of galaxies beginning to move toward each other under mutual gravitational influence. The attraction is real, but the acceleration is small. Over a human lifetime, the change in position would be imperceptible. Over millions of years, it becomes significant. Over billions of years, it reshapes entire regions of the universe. To the brain, this feels unsatisfying. Movement that cannot be seen might as well not exist. Gravity appears weak, indecisive, or absent. In reality, it is doing exactly what it always does. It is just operating on a scale that intuition was never designed to register. Clusters of galaxies provide a striking example. These vast collections contain hundreds or thousands of galaxies bound together by gravity. The motions within them are slow and subtle, yet they are sufficient to hold the cluster together over cosmic time. Individual galaxies weave intricate paths through the cluster, influenced by the combined mass of everything around them. From a human perspective, this motion looks frozen. From a cosmic perspective, it is dynamic and structured. The difficulty lies not in gravity's behavior, but in the brain's expectations. Human perception evolved to deal with immediate consequences. A falling object demands quick response. A moving animal requires instant attention. Slowness rarely signaled danger. As a result, intuition equates significance with speed. Gravity at cosmic scales violates this expectation. Its most important work happens gradually. Structures form not through sudden assembly, but through steady convergence. Over time, small influences add up to enormous effects. Astrophysicists studying galaxy formation often describe this process as hierarchical. Small structures form first. Over time, they merge and grow into larger ones. Gravity guides this process without urgency. It does not rush to completion. It allows matter to settle into stable arrangements through countless gentle interactions. This requires patience to understand. Patience is not just a personal virtue here, it is a conceptual requirement. Understanding gravity at these scales means letting go of the need for immediacy. It means accepting that meaningful change can occur over time scales that dwarf human history. The brain resists this because it is anchored to short spans. Seconds, minutes, years, even decades strain intuition. Millions of years feel abstract. Billions feel unreal. When gravity operates primarily across such spans, intuition disengages. This disengagement often leads to misinterpretation. Gravity is described as weak because its effects are not dramatic on short timescales. In reality, its strength lies precisely in its ability to act consistently over long durations. Other forces dominate brief interactions. Gravity dominates the long game. Stars burn brightly, but they eventually exhaust their fuel. Electromagnetic forces govern the interactions that make chemistry possible. Nuclear forces bind matter at its core. Gravity persists after all of these processes play out. It gathers remnants. It builds new systems from old ones. It shapes the large-scale architecture of the universe. This persistence is easy to overlook because it lacks spectacle. There are no flashes or shocks announcing gravity's work. Instead, there is motion so slow it appears static, and change so gradual it requires careful measurement to detect. Astronomical observations rely on this patience. Telescopes capture snapshots separated by decades. Patterns emerge only when data is compared across time. What initially looks like a static sky reveals itself as dynamic when viewed through the lens of long-term observation. The brain, accustomed to rapid feedback, struggles with this mode of understanding. It wants confirmation now. Gravity offers confirmation later. This mismatch feeds misunderstanding. If gravity does not act quickly, it must not be doing much. If it does not produce visible motion, it must be negligible. These conclusions feel intuitive, but they miss the point. At cosmic scale, slowness is not a flaw, it is a feature. Slow motion allows systems to stabilize, it prevents chaos. Rapid gravitational collapse would produce violent, short-lived structures. Gradual convergence allows galaxies to settle into long-lasting forms. It gives stars time to form and planets time to assemble. Slowness is structure's ally. This idea runs counter to everyday thinking, where speed often signals power. Fast machines feel impressive. Sudden movements command attention. Gravity's power is quiet. It is expressed through endurance rather than intensity. There's gentle irony in how often cosmic gravity is described using dramatic language. Galaxies collide. Clusters crash together. These events do occur, but even they unfold over millions of years. What is described as a collision is more like a slow interweaving, with vast distances between individual stars. Nothing smashes in the way intuition expects. Gravity choreographs rather than strikes. Understanding this requires adjusting the emotional tempo of thought. It asks the mind to slow down, to stretch its sense of cause and effect across unfamiliar spans. It asks for comfort with delayed outcomes. Scientific bodies studying large-scale structure often emphasize this shift in perspective. They frame gravity not as an agent of sudden change, but as the organizer of long-term order. Its influence is cumulative, shaping patterns that only become clear when viewed from far enough away in both space and time. For human intuition, this distance is difficult to maintain. It prefers stories with beginnings and endings close together. Gravity offers stories whose chapters are separated by epochs. Reframing slowness as structure helps bridge this gap. Instead of seeing gravity as ineffective because it acts slowly, it can be seen as effective because it does. Slow processes are less fragile. They are less sensitive to disruption. They allow complexity to emerge without tearing itself apart. The universe bears the marks of this patience. Galaxies persist for billions of years. Clusters endure even longer. The large-scale pattern of matter reflects gravity's steady guidance, rather than sudden intervention. Once this is recognized, the apparent stillness of the cosmos takes on new meaning. What looks calm is active. What looks frozen is evolving. Gravity is at work everywhere, but it works on its own schedule. The brain's expectation of immediacy is understandable. It reflects the environment in which human perception evolved, but that environment represents only a tiny slice of reality. Beyond it lies a domain where patience is not optional. Understanding gravity at cosmic scales means learning to think slowly, to allow processes to unfold mentally over spans far longer than a lifetime, to accept that significance does not require speed. Gravity does not hurry because it does not need to. Given time, it shapes everything. In that sense, gravity's greatest lesson at cosmic scales is not about force, but about tempo. It reveals a universe where the most powerful influences are often the quietest, and where slowness is not the absence of action, but the foundation of order itself. There comes a point where trying to picture gravity simply stops working, not because the idea is too advanced, but because imagination itself runs out of useful reference points. The mind is built to visualize things it can, at least in principle, sense. Shapes, motions, textures, boundaries. Gravity offers none of these directly. Imagination relies heavily on the senses. Even the most abstract mental images are assembled from familiar parts. When imagining an unfamiliar animal, the brain borrows features from known ones. When picturing distant places, it rearranges landscapes already seen. Visualization is not invention from nothing, it is recombination. Gravity resists this process. There is no color to borrow, no texture to adapt, no sound to attach. Gravity cannot be seen, touched, or isolated. Its presence is inferred through behavior rather than sensation. Objects move a certain way. Clocks tick at certain rates. Paths curve. The cause itself remains invisible. This invisibility places gravity outside the usual reach of imagination. The mind tries anyway. It reaches for arrows, fields, dents, flows. Each attempt feels temporarily helpful, then quietly misleading. The image holds for a moment before collapsing under closer inspection. Diagrams are often introduced to bridge this gap. Lines show forces, grids show curvature, arrows indicate direction and strength. These tools are invaluable for calculation and communication. They condense complex relationships into something manageable on a page. But diagrams are not pictures of reality. They are symbolic shortcuts. A diagram shows what matters for a particular purpose and ignores everything else. It is selective by design. When interpreted as literal, it creates false expectations. Arrows begin to feel like physical things. Curves begin to feel like shapes embedded in space. The diagram becomes the object rather than a guide to reasoning about it. This is why diagrams help without solving the deeper problem. They support understanding by structure, not by imagery. They tell you how quantities relate, not what gravity looks like. When the mind expects them to deliver a picture, disappointment follows. The failure here is not intellectual, it is perceptual. The human brain evolved to track objects moving through space, not to reason about space itself as an active participant. It expects causes to have locations and mechanisms to have parts. Gravity offers neither in a way imagination can comfortably grasp. This is where abstraction enters, often reluctantly. Abstraction is sometimes treated as a last resort, a sign that understanding has become thin or removed from reality. In truth, abstraction is one of the strongest tools science has. It allows patterns to be described without committing to imagery that may mislead. In the case of gravity, abstraction is not a compromise, it is an advantage. By focusing on relationships rather than pictures, abstraction avoids the traps imagination falls into. It does not ask what gravity looks like. It asks how mass, distance, motion, and time relate. It tracks behavior rather than form. This approach sacrifices visual comfort in exchange for reliability. Many physicists have pointed out that the most accurate descriptions of nature are often the least visual. Quantum behavior, probability, higher dimensional geometry, and space-time relationships all resist pictorial representation. They are understood through rules, constraints, and patterns rather than scenes. Gravity belongs firmly in this category. Trying to force a visual model where none fits can actually hinder understanding. The mind becomes attached to an image that works only partially. When new information conflicts with that image, confusion deepens. Letting go of the image allows understanding to remain flexible. This letting go can feel uncomfortable at first. Visualization feels like comprehension. Seeing something in the mind's eye creates confidence. Releasing that habit feels like losing grasp rather than gaining clarity. But understanding does not require pictures. It requires consistency. You can understand how something behaves without knowing what it looks like. People understand how electricity works in practice, without picturing electrons as tiny balls flowing like water. They understand how probabilities combine without imagining probability as a physical substance. The understanding lives in prediction and application. Gravity is similar. It can be understood as a set of dependable relationships. Objects accelerate in certain ways. Paths follow particular patterns. Time behaves differently under different conditions. These facts hold regardless of whether they can be visualized. Encouraging comfort with this kind of understanding is a shift in expectation rather than ability. It means accepting that some aspects of reality are not meant to be seen, even mentally. They are meant to be described. Descriptive understanding focuses on what changes, how it changes, and under what conditions. It does not insist on a mechanism that looks familiar. It values agreement with observation over intuitive appeal. This approach also aligns better with how science actually progresses. New theories often replace older pictures not because the old ones were useless, but because they were too specific. Pictures constrain thought. Descriptions allow expansion. There is gentle humour in how stubbornly people continue to ask what gravity looks like, as though it might eventually reveal a shape if pressed hard enough. The question itself assumes that all aspects of reality must conform to visual intuition. Gravity quietly refuses. This refusal is not hostility, it is honesty. The universe does not organize itself for human imagination. It organizes itself according to relationships that remain consistent whether or not they are pictured. The mind's task is to adapt to those relationships, not to demand that they resemble familiar scenes. Letting go of seeing gravity does not mean giving up on understanding. It means shifting the goal. Instead of aiming for a clear image, the aim becomes a clear sense of behavior. What happens if mass increases? What happens if distance changes? How motion responds? How time is affected? These questions can be answered precisely without ever forming a picture. Over time, this kind of understanding becomes comfortable. The absence of imagery stops feeling like a gap and starts feeling like space. Space for ideas to connect without being forced into shapes they do not fit. This shift also reduces frustration. Many people assume that if they cannot visualize something, they have failed to understand it. In cases like gravity, the opposite is often true. Letting go of visualization can be a sign of deeper comprehension. The mind learns to trust descriptions rather than scenes. It learns to recognize patterns without demanding form. It becomes less attached to metaphors and more attentive to consistency. Gravity does not need to be seen to be known. It needs to be recognized through its effects, through the regularity of motion, through the reliability of prediction, through the quiet way it holds systems together. Understanding in this sense becomes quieter too, less dramatic, less satisfying in an immediate way, but more stable over time. The failure of visualization is not the end of comprehension. It is a transition point. a moment where intuition hands responsibility over to a different way of knowing. Once that handoff is complete, gravity stops feeling elusive, not because it suddenly becomes clear, but because clarity no longer depends on imagery. Descriptive understanding does not demand pictures, it demands coherence. Gravity offers that coherence generously. It behaves the same way everywhere. It follows the same rules regardless of scale. It remains consistent even when imagination falters. Accepting this allows understanding to deepen without strain. The mind no longer needs to see gravity to trust it. It can let patterns speak for themselves, and in doing so, it discovers that some of the most reliable features of reality are not those that can be pictured, but those that can be described, tested, and depended upon quietly, without ever appearing in the mind's eye at all. Understanding is often mistaken for familiarity. If something feels intuitive, it is assumed to be understood. If it feels strange or abstract, it is treated as unresolved. This expectation runs deep, shaping how people judge explanations long before accuracy enters the conversation. Gravity exposes the weakness in this assumption. People predict gravity successfully every day without thinking about it. Objects dropped from a hand will fall. Steps must be placed carefully to avoid slipping. Lifting something heavier requires more effort. These predictions are reliable, automatic, and effective, yet none of them require a clear mental picture of what gravity is or how it works. This reveals an important distinction. Prediction and intuition are not the same thing. Intuition feels like understanding because it is comfortable. It aligns with experience. It requires little effort. Prediction, on the other hand, is about reliability. It asks whether an outcome can be anticipated correctly, regardless of how satisfying the explanation feels. Science is built around prediction, not comfort. When scientists judge a model, they do not ask whether it feels natural. They ask whether it works. Does it produce results that match observation? Does it remain consistent across situations? Does it allow new phenomena to be anticipated before they are measured? Gravity passes these tests extraordinarily well. Its behavior can be predicted with remarkable precision across an enormous range of conditions. From falling objects to planetary motion to the timing of satellites, gravity behaves exactly as described, even when the description resists intuition. This is why science places accuracy above comfort. Comfort is subjective. Accuracy is measurable. A comfortable explanation that fails to predict is not useful. An uncomfortable explanation that succeeds is. Over time, the latter earns trust, even if it never becomes intuitive. This approach can feel unsatisfying to those seeking a clear mental picture. It can feel like settling for something incomplete. But this feeling arises from a misunderstanding of what scientific models are meant to do. Models are tools, not mirrors. They are not attempts to recreate reality in the mind. They are frameworks for organizing information and making predictions. A good model captures what matters for a given purpose and ignores what does not. It simplifies, not to deceive, but to function. Consider a map. A road map does not show every tree, building, or contour. It shows what is needed to navigate. A weather map does not show streets or landmarks. It shows patterns of pressure and temperature. Neither map is a full picture of reality. Both are extremely useful. Gravity models operate in the same way. They describe relationships between mass, distance, motion, and time. They do not attempt to depict gravity as an object or substance. They do not claim to show what gravity looks like. They show how it behaves. Expecting more from them is like expecting a map to resemble a photograph. The disappointment comes from a category error, not from a failure of the model. This perspective allows understanding to be redefined. Understanding does not mean holding a vivid image. It means knowing what to expect. It means being able to reason about outcomes. It means being able to apply principles reliably. In this sense, understanding gravity can be entirely operational. Engineers understand gravity well enough to design bridges, towers, and vehicles. Astronomers understand it well enough to predict eclipses and spacecraft trajectories. Physicists understand it well enough to correct satellite clocks so navigation systems function accurately. None of these applications require a comforting mental picture. They require dependable rules. The discomfort many people feel arises from a mismatch between expectation and reality. There is an expectation that deep understanding should feel like clarity in the imagination. Gravity offers clarity in prediction instead. Once this shift is accepted, much of the frustration dissolves. There is no requirement to see gravity in order to trust it. There is no requirement to imagine curved space in order to use it. The success of the model is the understanding. This reframing also helps explain why multiple models can coexist without contradiction. Each model serves a purpose. Each highlights different aspects of behavior. None claims to be the final word. Science values this flexibility. It allows descriptions to evolve without being mistaken for absolute truth. Models can be refined, replaced, or limited in scope without undermining what they already explain well. This humility is not weakness, it is discipline. The insistence on mental pictures often comes from a desire for closure. Pictures feel final. They suggest that nothing important has been left out. But reality rarely offers such neat conclusions. Clinging to imagery can actually slow progress by locking thought into forms that no longer fit. Letting go of the need for pictures frees understanding to deepen without resistance. This does not mean abandoning intuition entirely. Intuition remains valuable for navigating everyday life. It provides quick, effective guidance where precision is unnecessary. But it does not need to govern all domains. Gravity operates beyond the scale where intuition evolved to function. Asking intuition to dominate there is like asking eyesight to detect radio waves. The limitation lies in the tool, not in the phenomenon. Recognizing this helps reframe confusion. Difficulty imagining gravity is not a failure to understand. It is a sign that understanding has moved into a different mode. There's gentle humour in how often people apologise for not being able to picture gravity, as though they have missed a step. In reality, many of the people who understand gravity best report thinking in terms of relationships rather than images. Their understanding is no less real for lacking pictures. The demand for visualization is cultural rather than scientific. It reflects how learning is often presented, not how understanding actually works. Operational understanding also has an emotional benefit. It reduces anxiety. There is no longer pressure to achieve a sudden moment of insight where everything snaps into focus. Understanding becomes gradual, cumulative, and stable. Gravity behaves the same way it always has, regardless of how it is imagined. Trust grows from consistency, not from imagery. This trust allows the mind to relax. The need to resolve every abstraction into a picture fades. What remains is a quiet confidence in patterns that hold. Science does not promise comfort. It promises reliability. In return, it asks for a different kind of acceptance, an acceptance that models are provisional. That understanding can be functional rather than visual. That clarity does not always feel like familiarity. Once this acceptance settles in, gravity no longer feels like a problem to be solved. It becomes a case study in how understanding actually works. Prediction replaces imagery. Consistency replaces comfort. Description replaces depiction. This does not diminish the wonder of gravity. It changes its texture. The mystery shifts from what gravity looks like to how consistently it shapes the universe. And in that shift, understanding becomes quieter, more resilient, and less demanding. Gravity does not ask to be imagined correctly. It asks to be taken seriously. It asks to be described carefully, tested rigorously, and trusted where it proves reliable. Meeting those requirements is what understanding actually means. Living with gravity does not require understanding it. This may be the simplest and most overlooked truth about the human relationship with the universe. Gravity has shaped every moment of life on Earth long before anyone attempted to describe it. Bodies stand, oceans stay where they are, planets follow their paths. None of this waits for comprehension. Gravity is reliable in a way few things are. It does not surprise, it does not switch off, it does not depend on belief, interpretation, or mental clarity. Whether it is imagined as a pull, a curve, or something else entirely, it behaves the same way. Confusion about its nature does not weaken its effect. Misunderstanding does not disrupt its consistency. This reliability is easy to miss because it is so complete. Humans function perfectly well without knowing what gravity is. Children run, climb, and fall with no concept of mass or acceleration. Animals navigate terrain with remarkable precision, without theories or equations. Even adults who have never studied physics rely on gravity successfully thousands of times a day. Movement, balance, and coordination all work without explanation. This reveals something important about how humans relate to the world. Survival and function do not require deep conceptual understanding. They require dependable patterns. Gravity provides those patterns generously. The mind often assumes that lack of understanding implies vulnerability. If something cannot be explained clearly, it feels dangerous or unstable. Gravity challenges this assumption. It remains one of the most predictable aspects of reality, despite resisting intuitive explanation. This contrast can be unsettling at first. It seems to suggest that the universe does not care whether it makes sense to human minds. In a way, that is true. But it also suggests something reassuring. The universe does not demand comprehension in order to remain stable. Humans coexist with countless processes they do not fully understand. The body regulates temperature, balances chemicals, and repairs tissue without conscious oversight. Technology relies on layers of systems that most users never examine. Electricity flows, signals transmit, structures hold. Life proceeds. Gravity belongs to this category. It is part of the background architecture of existence. Its role is structural rather than dramatic. It holds systems together quietly, without asking for attention. Misunderstanding gravity, then, is not a problem to be solved. It is a condition to be accepted. This acceptance does not mean giving up on learning. It means reframing the goal. Instead of aiming for complete intuitive clarity, the aim becomes coexistence with something that works reliably, even when it feels strange. In this light, confusion stops being a failure. It becomes a natural response to scale and abstraction. Gravity operates across domains far removed from everyday experience. Expecting intuition to handle that seamlessly is unreasonable. The brain evolved to navigate surfaces, avoid falls, and maintain balance. It did not evolve to picture curved space or time dilation. When it struggles with those ideas, it is not malfunctioning. It is encountering the edge of its design. Recognizing this boundary allows tension to ease. There is no longer pressure to force understanding into a familiar shape. Gravity can remain unintuitive without being threatening. Stability does not require comfort. Scientific institutions often emphasize this distinction when communicating complex ideas. They highlight that certainty in behavior can coexist with uncertainty in interpretation. Models can work even when their deeper meaning remains open to discussion. Progress does not depend on resolving every conceptual difficulty. This perspective aligns well with everyday experience. People trust gravity implicitly without analysing it. They trust the ground to support them. They trust objects to fall when released. This trust is earned through consistency, not explanation. The same trust extends outward. Planets follow predictable paths. Satellites remain in orbit. Seasons unfold with regularity. Gravity's role in these patterns is steady and dependable, even if its description evolves. There's gentle irony in how much anxiety gravity's unintuitive aspects provoke. Something so constant and reliable is rarely questioned until its explanation becomes strange. The strangeness arises not from gravity itself, but from the mismatch between human intuition and cosmic reality. Reframing misunderstanding as coexistence helps restore balance. Gravity does not need to be mentally conquered. It does not require a final picture. It simply needs to be acknowledged as a stable feature of the world. This reframing also shifts attention away from mystery and toward continuity. Gravity is not mysterious in its effects. It is mysterious only in its deeper description. Day to day, life depends on the former, not the latter. The universe, viewed this way, is not chaotic or unsettling. It is orderly, even if that order does not always align with intuition. Stability emerges from rules that operate consistently, not from explanations that feel comfortable. Living with an unintuitive universe therefore becomes an exercise in humility rather than fear. It invites an appreciation of how much works without demanding understanding. It encourages patience with concepts that resist simplification. Humans have always lived this way. Long before theories of gravity, people built structures, navigated landscapes, and observed the sky. Understanding followed practice, not the other way around. Even today, understanding remains layered. Practical knowledge comes first. Conceptual refinement follows. Complete clarity may never arrive, and that is acceptable. Gravity continues to act whether it is imagined correctly or not. It supports bodies, binds systems, and shapes motion with unwavering regularity. The mind can struggle while the universe remains calm. This calm is worth noticing. In a world where uncertainty often feels threatening, gravity offers a counterexample. It shows that something can be deeply unintuitive and profoundly stable at the same time. It demonstrates that reliability does not depend on comprehension. This realization carries beyond physics. It applies to many aspects of existence. Not everything that matters needs to be fully understood. Some things only need to work. The universe is full of processes that exceed intuition. Time behaves strangely, space stretches, matter forms patterns that defy simple explanation. Yet life persists within this complexity, supported by underlying regularities. Gravity is one of those regularities. It does not demand to be solved. It invites acceptance. As understanding deepens, confusion may remain, but it becomes quieter. It loses its edge. It no longer signals danger or failure. It becomes a companion to curiosity rather than an obstacle. Living with an unintuitive universe means learning to trust patterns over pictures, to value consistency over clarity, to recognize that stability does not require full transparency. This trust does not dull wonder. It refines it. Wonder shifts from trying to force reality into familiar shapes to appreciating how well it functions without doing so. Gravity holds everything together without asking to be imagined. It does its work silently, patiently, and impartially. The universe rests on its reliability, not on human understanding. Accepting this allows thought to settle. There's no rush to resolve every abstraction, no urgency to eliminate every unanswered question. The universe is not waiting for permission to continue. In that sense, living with gravity becomes a lesson in coexistence. Humans inhabit a world shaped by forces they do not fully grasp, yet rely on completely. This is not a flaw in existence. It is a feature. Gravity will continue to guide motion tomorrow exactly as it did yesterday. The earth will remain beneath the feet. The sky will remain above. The quiet stability of the universe will persist. Understanding may deepen. Descriptions may change. Intuition may adapt slowly. But gravity will remain what it has always been. Reliable. Unfazed by confusion. A steady presence in an unintuitive universe that works remarkably well all the same. Gravity began this journey as something familiar and uncomplicated, a force felt every day, trusted without question, rarely examined. Along the way, that familiarity loosened. What once seemed obvious revealed layers of strangeness, abstraction, and resistance to intuition, and yet nothing about gravity itself ever changed. It continued to work. Objects still fell when released. Bodies remained supported by the ground. Planets followed their paths. Time ticked on, slightly differently in different places, but always consistently. Gravity did not pause while explanation struggled to keep up. It did not wait for a clear mental picture to emerge. This returns us gently to the original question. Why can the human mind struggle so deeply with something so fundamental? The answer does not lie in a flaw of intelligence or curiosity. It lies in the nature of intuition itself. Human intuition evolved to keep bodies balanced, to avoid falls, to navigate surfaces and edges. It was never designed to account for curved space, time dilation, or motion unfolding over billions of years. Expecting it to do so effortlessly places a burden on it that it was never meant to carry. Not understanding gravity in an intuitive way is not a failure. It is a natural consequence of scale. Science does not require intuition to feel satisfied in order to be valid. It requires consistency, evidence, and predictive power. Gravity meets those requirements completely. Its behavior is among the most precisely described features of the universe, even as its deeper nature continues to invite discussion and refinement. This coexistence of reliability and mystery is not unsettling once it is recognized for what it is. The universe does not demand comprehension as a condition for stability. It does not collapse when understanding lags behind description. It continues calmly, governed by patterns that hold whether or not they are imagined clearly. In this sense, gravity offers reassurance rather than uncertainty. It shows that something can be deeply unintuitive and entirely dependable at the same time. It demonstrates that clarity of behavior matters more than clarity of imagery. The ordered nature of the universe does not rest on human understanding. It rests on relationships that remain steady across time and space. Gravity is one of those relationships. It binds systems together quietly, without spectacle, without explanation, and without interruption. Living within such a universe does not require mastery of its deepest principles. It requires trust built from consistency. Humans have always lived this way. Long before theories existed, gravity shaped lives reliably. Long after descriptions change, it will continue to do so. The discomfort that arises when intuition fails is understandable, but it does not signal danger. It signals a boundary between experience and abstraction. Crossing that boundary does not require forcing understanding into familiar shapes. It requires patience, humility, and a willingness to let some questions remain open. In the end, gravity does not ask to be fully grasped. It does not demand to be pictured, named, or resolved. It simply continues to act, holding worlds together with quiet certainty. The universe, viewed this way, is not something that needs to be conquered intellectually. It is something that can be lived within, observed, and trusted. Its order does not depend on comprehension. Its stability does not depend on intuition. There is comfort in that. Gravity works. It always has. it will continue to do so regardless of how it is imagined, and in that steady reliability lies a calm reminder that understanding is not always about knowing everything, but about recognizing what can be depended upon. The universe does not require complete understanding to remain whole. It asks only that it be allowed to be what it is, and that is enough to rest with.